Okay, sorry about that earlier, guys. I started coughing. You know when you start coughing and you can't stop. I swear I don't have the coronavirus, but you know. Anyway, um so I stopped here and I just wanted to explain something really quick just because I started to think about um it a little. So we have this as our free body diagram. If I can get over to it. I'm trying to go backwards and I can't for some reason. But it looked like this. This was our free body diagram. Well, we did the tensional force in the y direction with the weight. We're not given the force going this way. And I just did like the tension sine theta, and I wanted to explain why, because if you have this force right here, this is your not E. Sorry. That would be your force in the x direction. Sorry, my dogs are barking in the backyard if you can hear them. Minus your tension sine theta is equal to 0. So this is minus because, like, if this was your origin right here, that would be going in the negative x direction. So when you move that over, it becomes your force of x is equal to tension sine theta. So if you were wondering why that was that, that's why. So I just wanted to point that out and just let you know what was going on there, just in case. Okay, so we are on the move again. All right, so electric field due to a point charge. And so that single little point charge can be found using Coulomb's law. And so just remember that Coulomb's law is K, and then you've got this point charge, which is really just supposed to be this like teeny tiny little charge that you put just to kind of see what the electric field is at that point. That's its purpose, like at a certain distance or point from the main source of charge or the big charge. I know, I'm using the same letter. One's lowercase, one's uppercase. I can almost see your faces right now. And basically the whole purpose of this is really just to find what the electric field is at that certain point. Okay? So if I take this Coulomb's law right there and I plug it in for that force, so I've got all these things and I'm still keeping Q on the bottom here. Well, look what happens to one of these. Okay, so you're able to figure out what the electric field is, you know, at that particular point. Okay, so you can actually combine that equation, that Coulomb's equation, to that electric field equation. And what ends up happening is you end up getting this. Okay? Alrighty. So we are on example 16.6 now. So this says 2 point charges, that sounded weird at first, are located on the x-axis. Charge Q1 is plus 0.6 microcoulombs. It's located at x equals 0. Charge 2 is negative 0.5, located at 0.4 meters. Point P is located at 1.2. Okay, so this is sort of your point charge. And it's saying at that point, what is the electric field and direction? Okay, due to the two charges. Now, this is where I don't really agree, I guess, because I wish they would have given this other lesson that comes like a few slides away before they would have given this example. And basically just to know that the with electric fields, they're always going towards the negative charge and they're always going away from the positive charges, okay? So you know you're going to have an electric field that's going like this and you're going to have one that's going like this because you're not only getting the electric field from that one, you're also getting the electric field from that one, okay? So you have to kind of keep that in mind. whenever we're doing this. All right, so let's write some information down. So we've got Q1 is plus 0.6. I really should have written a 0 there. I don't really like that. You guys know what I'm talking about, but oh well. I'm gonna try to be as neat as possible. At x equals 0 meters, okay, Q2 is your negative 0.5 microcoulombs, and that's at x equals 0.4 meters. And then that point right here, right, is 1.2 meters away. All right, so let's do electric field 1 first. All right, so electric field 1. All right, so that is this point charge, okay, due to this right here. All right, because that's this point, that's that electric field that's being pushed away, because the electric fields on a positive charge are going away from it. They're going outside, and you'll see that here in a couple of slides. Okay, like I said, I wish they would have done this a couple slides before. Oh well. So we've got force over Q, which on the previous slide we said if we use, Coulomb's law and we plug it in for that force, then we end up getting this right here. So now, do we have all of this information? Yes. We've got Coulomb's constant. We've got the charge. And micro is -6. We've got the distance, which is 1.2 meters, and it's squared. So keep that in mind. And you end up getting, oh, and this was positive, by the way. So you end up getting plus 3.75 times 10 to the third newtons per coulomb. Okay? Now, why was it 1.2? Because that's that point from this x equals 0 point, okay? So you got to add all of this, right? That total distance. All right, so now let's do electric field 2. All right, so that is, that's due to this guy right here. That's this point due to that one right there. So the electric fields are always going to point towards the negative charges. All right, so we've got the same equation, just some different numbers. So we've got Coulomb's constant multiplied by the negative charge now. And now what's the distance from the P over to this negative Q2 here? Well, it's this 0.8 meters right here. So you've got 0.8 meters squared. So you end up with negative 7.02 times 10 to the third, yes, newtons per coulomb. That's a newton, but it doesn't look like it. Okay, I gotta go over to the next slide because I've run out of room here. Okay. So now you're basically just getting the sum of the electric field. So, I mean, and if you look back at the question a couple slides before, it says what's the magnitude and the direction of the electric field. So the magnitude is just the resultant, right? So you got to do the sum, which typically when we've done the sum of vectors, we've got them going in all different directions. Well, here we've got them going in just the x directions, okay? Which makes it actually easier, because we can just say negative 7.02 times 10 to the third newtons per coulomb plus 3.75 times 10 to the third newtons per coulomb. And you just get the sum, which is negative 3.3 times 10 to the third newtons per coulomb, which all that negative is telling you is that it's in the negative x direction. Remember how those negatives in vectors are just telling you the direction. So like when we had a negative velocity, it was just basically saying it was going to the left or it was going west or south or something. That's exactly what that negative is doing in this electric field situation. It's just telling us that the sum of it is more in the left than it is going into the right. Okay? Which should make sense because that P is closer to that negative charge than it is to the positive one. Even though the positive one is a bigger charge, the distance away really matters more, because if you look at that equation for electric field, the R, the distance, is being squared. So that really does affect it. All right, so that is example 16.6. All right, so we have another example for 16.7, and I'm just a little bit worried about time. I mean, I can have a longer time on YouTube videos, it's just not, they don't like it. So I'm just going to go ahead and stop at this one, and I'll start up again.